All right, finally, for the last part of our first lesson in the normal distribution here, here's a word problem that probably is going to model the majority of the word problems for you in your homework. So again, at this point in the process, I just want you to be able to identify it and then apply it. And then in the next lesson, we're going to talk about using some critical thinking skills and moving on, using it in the big picture. So bolts are manufactured at 55 millimeters, and there's a 2 millimeter standard deviation. So whenever you mass produce something, bolts, nuts, it could be anywhere from shocks for cars to brakes, they're not all going to be exactly identical. There is going to be some deviation in measurements. So the information provided here, it tells me that 55 millimeter is the average, the mean, and there is a deviation, so that means that our bolts here are normally distributed, and I know that's 55 millimeters is the mean and 2 millimeters is the deviation. So that's what that first sentence tells me, okay, that information right there, and it's needed in order to answer the rest of the questions. So determine the percentage of bolts that are produced when. So A part. What happens if they are, what's the probability they're longer than 55 millimeters? So this is where a sketch is going to help you out off the start, and eventually people are going to get to the point where they don't need it. Okay, here's the normal distribution. Most bolts are 55 millimeters. 59's over here somewhere, and we want to know the percentage that is longer, which means we want this area. Now remember, the Z-score information that we get finds this area. So if we want to find the probability that a bolt is going to be greater than, longer than 59 millimeters, okay, we have to do the indirect approach here. We know that the area under the curve, and this goes back to the properties in the first segment or the first video of this lesson, the area under that curve is equal to 1. The chart tells me this area, so I need to take the whole area and I want to subtract the probability of x being less than 59 because I want the area above that. So I'm taking what I can find. I can find this in my Z chart, okay, the Z-score table. I can find that information, and I know that if I take it away from 1, what's left over is what I need. Okay? So off to the side here, for A part, I have to find a Z-score. So again, the Z-score, x minus x bar, or mean divided by standard deviation. So we're dealing with a 59 millimeter bolt. We're going to take away 55, and we're going to divide that by 2. So 59 take away 55 is 50, or it's 4, divided by 2 is 2. So we're looking for a Z-score of 2. So what this now becomes, I'm going to convert my variable notation to a Z-score notation. So this is the exact same as me saying, what's the probability, or what's the value when Z is less than 2? So those are equivalent expressions, okay? One is in terms of the actual measurements of the data, okay, so 59 millimeters. Now that 59 millimeters has been converted to a Z-score of 2. So to finish solving this, I just need to look up in my Z chart, or Z-score table, what is the corresponding area for a 2. So pulling up or pulling out your sheet, we look for 2.0. Here's the 2.0 right there, and that's the information we want. 0.9772, and going back to this, we get 0.9772, and when you finish that calculation, then it's the 1 minus 0.9772, we get 0.0228. So if you're looking through a bin of bolts, therefore, there is a 2% chance of finding a bolt 59 millimeters or longer. All right. So there we go. That's how you would calculate it using that indirect approach. So this is the area we wanted. That's the 2% or the 0.0228. And we did it by taking this area and subtracting it from 1. So that occurs when you're looking for something greater than. Okay. B part. What's the probability that they are shorter than 54? So again, I'm going to start with the diagram so it's a little bit easier for you to visualize. Here's my 55. 54 is right there. And because I want shorter than, that means I'm looking for all the bolts on this side. And this is a good thing because that's what my Z score chart calculates, the area from a point down to the bottom. So I can calculate my Z score. I'll do it up here using similar information. This time I want 54. Take away 55 divided by 2. That's negative 0.5. So the probability that a bolt is shorter than 54 is equal to, in this case, it's the area I want, so I can go straight to a Z statement, a Z score statement, and that's the same as saying a Z score that's less than negative 0.5. Okay, so these are equivalent statements. All right, they're equivalent statements. One is dealing with the actual data value, the other one is dealing with Z score value. Because it's the area that I want, I can go straight to our Z score, and we're looking for, in the Z score chart, negative 0.5. So there are my negatives. Oops, I probably went by it right there. So here's negative 0.5. And remember, it's really negative 0.50. So this is the one I want. So I want to take forward 0.2776. So, oops. There we go. So 0.2776. So therefore, the probability will be 27.8%. It is shorter than 54. All right. Oh, 54 millimeters. Okay, so it deals with the area underneath. The last one then, this is the one where the diagram will help. So we're looking between 53 and 57. So for C part, give ourselves a diagram here. So here is my normal distribution. We said 55 is in the middle. And I want 53 to 57. Okay, so this will be the trick here of the questions. So here's 57. Here's 53. This is the area that I want to calculate right here. My Z-score chart does not calculate this area. Okay, it does not calculate this area. If I put 57 into the Z-score formula, so if I was to calculate this value right here, same as what we did before, 57 minus 55 over 2, I get a Z-score of 1.00. If I want to calculate, or if I want to then go to my chart, that will calculate, or that gives me this area of the curve. So the green is what I would have by doing that calculation. I want the blue. If I then use the 53, x minus x bar, and I'm hoping a couple people are starting to see where I'm going with this. So 53 minus 55 over 2, I would end up with negative 1.00. However, that, if I went to the chart, will calculate the red area. Okay, so I'm going to oversimplify this for this example so that you can see what I'm doing. So the question is, in terms of area, so I'm going to do it in terms of area, what does blue equal? So here's my original blue. All right, my blue is right there. What does blue equal? Well, blue is equal to green minus red. So if I take away that red component, so if I was to take away that red component right there, then I would be left with this area right there. Okay? So translating that into math terminology. So in math, and you can work an area. I'm quite happy with that until you get comfortable with it. I always appreciate people that simplify it down to show that they understand what they're looking for. So what does blue equal? Blue is the probability that our value is between 53 and 57. That's the blue. All right, so 53 is smaller than x, but x is smaller than 57. What's my green area? Green is the probability that x will be smaller than 57 minus the red area, x is going to be smaller than 53. Now we already have the z-scores, so we can convert that to z-scores. So the 57 is 1.00, and the other one, the 53, is negative 1.00. Now we go to our z-score chart, and we can replace those values. So as soon as you're dealing with a z-score, you can use your z-score chart. Okay, you have to be in z-score form in order to use that z-score chart. So let's look up the value for 1. So positive 1 is down here. Positive 1 is 8413. Here we can see if I remember those numbers. 0.8413. So that would be the blue region, or sorry, the green region, minus negative 1. Moving up. Negative 1. There it is there. Negative 1. 1379. 1379. One more time. 1379. And here we go. So now we've started with something simplified. Okay? So we want blue area. It's green minus red. We then take that and we convert it into a mathematical equation for us. Okay? And now it's just a simple calculation. Once we've pulled the information from the chart, 8413 minus 1379. So 0.7034. So therefore, the probability volts will be between 53 and 57 millimeters is 70%. So big picture, how do companies view this or look at this? Larger companies are asking themselves, is this a fair enough tolerance? If you're talking about building a construction building, 70% of your bolts between that range, that's probably all right. That's probably not a bad thing. However, if you are looking at building something more precise, so I mean, let's look at the International Space Station. Let's say the tolerances are much more tighter. That would maybe unacceptable. So it depends on the job that you're looking at. And most companies, when they sell a product, they will give you the guarantee in what range are we looking at for a particular length or quality of a product. So this really ties to quality control. And if you have any relatives or friends that are involved with quality control, that's what they're concerned with primarily. So here's your homework. Again, all you're doing today is you're identifying, yes, this is a normal distribution, and this is just the base skills. We're just practicing base skills on being able to apply it. So it's going to be conceptually a challenge. If you're able to get your head wrapped around the fact that probability is the area under the curve, then you'll be off to the races, because after that it's just a process on finding the correct values. So good luck.